Hi, this is Dave Erickson, and I've been working on another project that I thought I'd like to share. This is a quad SMU. It's a 4-channel source measure unit. It's based on a single chip 4-channel parametric measure unit, PMU, from Analog Devices. And this chip is intended for the semiconductor industry, and it provides current and voltage sourcing, current and voltage measure, and clamping on 4 simultaneous channels. The image you see here is what I have in mind as far as packaging is a mainboard which contains the AD5522 chip and all its support circuitry. Here's a processor. Here's the power supply. It's an AC powered power supply. On the front there's a front panel board with an encoder and buttons and a display. AD5522 is a pretty powerful chip. Let's get into the block diagram for the AD5522. This is one channel of the source measure unit, and there are 4 of them on the chip. And what we see, it starts with a force DAC, and that's a 16-bit D to A converter with some scaling. That goes into the force amplifier, and then the force amplifier through the internal range select feeds the force output, which feeds the device under test. And there are 5 current ranges. 4 of them are internal. The low current range is up to 2 milliamps, and then the 5th current range uses this additional buffer here, and this pin, the XFOH, drives an external R-sense, and the reason for that is because it's impossible to make precision, stable, low resistance resistors. This resistor is external, and it's about I think it's 20 ohms on my design. This is the current sense amplifier with a gain of 5 to 10, and it's an instrumentation amplifier, and it either senses through S4 and switch 4 and switch 6 across the internal resistor, or switch 8 and switch 9 across the external resistor, depending on what current range you're in. Down here, the DUT voltage is sensed here through the measure VH. I call that sense high. And then there's a signal called DUT ground, which is sense low, and then this instrumentation amp senses the voltage across the DUT and measures the difference between the plus and the minus. And then switch 10 here determines whether the current or the voltage gets fed back to the force amplifier. So in one way the system is a force voltage, and in the other way it's force current. In addition, the 2 measure amplifiers go into this multiplexer, the measure output mux and gain, and through an enable switch to make the measure output signal. And the measure output signal is used to drive the A to D converter, which measures the either the voltage or the current. Typically you will force voltage measure current, or you will force current measure voltage, although you can measure both. So we covered most of the analog circuitry here. In addition to the force DAC, there are 2 clamp DACs, clamp low and clamp high, and those are used to set clamp levels for either clamping current or clamping voltage, and those are also 16-bit DACs. And one of the unique things about this chip is that it has hardware offset and gain calibration for every range and for all 3 DACs. So if you look behind the force DAC, for example, you'll see 6 X2 registers, 6 X1 registers, 6 M registers, and 6 C registers. The X1 is what you use to set the voltage or the current, and there's 6 of them for the 6 ranges, 1 voltage range and 5 current ranges. The M register sets the gain, and that gets multiplied by the X1, and the C register sets the offset, and that gets added to the added to the product of the X and M registers. And then that gets stored in the X2 register. And that's what drives the DAC. And this is what gives the chip its precision. Those offset and gain calculations could be done in software before you set the register. In fact, they can be done. You can just set M and C to default values and do the calibration in software. But the chip is designed to be fairly high speed. So in other words, you set everything up once, and then when you switch ranges, it automatically calculates the offset and gain and does the calibration for you. There are 2 registers for the clamp high and 2 registers for the clamp low. The clamp high, there's 1 for voltage and 1 for all the current ranges, and the same with clamp low, 1 for voltage and 1 for all the current ranges. In addition, there's a whole set of registers down here which feed these 2 DACs. Notice those 2 DACs feed these 2 comparators and those 2 output signals on pins. And those are the compare high and compare low. So if you're building this into an ATE system, you'll want to know very quickly whether your measure value is within the high and low limits. And so you set these 2 DACs, and again, those are set by registers with offset and gain calculations in hardware, and those 2 allow you to very quickly compare the measured value to expected limits and see if they're within limits or not. I probably won't use that. That function can easily be done in software at a slower speed by just measuring the output of the A to D and then comparing it to limits. So I probably won't use that capability. Down on the left we have the serial interface, which is a standard SPI, serial clock, data out, data in, sync. A serial interface, by the way, can be LVDS or SPI, single-ended, and I just use single-ended. I don't have a need for LVDS. Some of these pins over here, the comparisons, the extra comparison pins, those also can be, are dual function. They can be either part of the LVDS interface, the differential signals, it requires two pins for differential, or they can be comparison outputs. So you can see it's a pretty full function precision PMU, and there's 4 of these on the chip, which is pretty impressive. Oh, one additional thing, I have it blocked up here. Let's see if I can scroll down. There we go. These 2 pins, sysforce and syssense, notice one of them uses a low resistance switch to the force pin, and there's one of these on every channel, and the other one uses a fairly high resistance switch to the sense or the measure channel. So the way sysforce and syssense are typically used is that these will drive a multimeter or calibration hardware so that you can quickly calibrate all the channels within a system. And there's only one sysforce and one syssense, and each channel has one of these switches. So these signals are common to all 4 channels. And my plan is to use those for calibration when I get the software at the point where it can control an external multimeter. So I'll use an external multimeter, for example, to measure the force, and then set the cal values until the outputs have the right precision. One last function: there are 2 compensation capacitors. One goes from here to C comp to ground, and the other one goes from CFF. That's a feedback. Notice that that's a capacitor that's across the shunt resistors, and that's like a feed-forward capacitor for doing compensation. And depending on the capacitive load, you may have to vary that capacitor. And I have provisions on the board for allowing 2 different settings for the compensation. So here's the block diagram for the original system using the evaluation board. So this block here is the AD5522 eval board. Notice the USB and the Cypress CPU that are on the board are not used, but notice there's an enable that enables the control from the CPU. And if you disable that, then all the functions of the board can be accessed through the 30-pin connector, all the digital functions. So here's the quad PMU chip. Here's the A to D converter. I chose the AD5685 ADC, which is the same ADC that's used on the evaluation board. And in fact, I have some previous experience with this ADC as well. It's a fairly pricey part, but it's fast. It's a 16-bit, 250 kilohertz. So you can switch between channels very, very quickly. And also it's fast enough so that if you want to read multiple readings and average, it does that nicely as well. The reference, a 5-volt reference, is an ADR435, which is a precision 5-volt, 3 parts per million reference. My original plan was to install headers as a connector between the motherboard and the daughter board. So the motherboard would have the connectors to bring out all the channels, and then I had to add wires to the board. So between the wires on the board, the fact that the board that I have is a pad down and I prefer the pad up, and the fact that there's no good mechanical mounting, and the fact that there's a bunch of extra parts that weren't going to be used, I ultimately decided to eliminate the eval board. And so the new board, when I draw the block diagram, it will not have the USB, the Cypress, this, or the wire app headers, or this board outline. It will have everything else though. It won't have the 30-pin connector. That's no longer necessary. So I wanted to use a 32-bit Arduino compatible CPU module, and I ended up with the Adafruit itsy bitsy M0 module. And I like that one because it's fast and it's fairly low cost. It's $12 for the plug-in module, and it's readily available from Arduino, and it's going to talk USB to the outside world. And that CPU controls the LCD. If I want to use an LCD, it will control that through the serial port. But also, currently I'm using the OLED display through the SPI, so that's shared against the SPI. It has GPIO to access the buttons and the encoder, and GPIO also to control the fan. Board also takes in plus or minus 15 volts, and those are isolated. So those come from either a lab supply, or I built a low noise power supply board to feed this. And then there's a 5-volt regulator, because the AD5522 and the A to D require 5 volts. And then there's an isolated 15 volt to plus 5 volt, so that the Arduino, the Arduino has a USB, so that needs to be grounded. And there's no reason not to ground the LCD, the buttons, and all that hardware. So pretty much everything on the left side and the top is isolated. For a power supply, I like the split core AC transformers because they have low common mode noise. I measured a couple of microamps of common mode noise, which is pretty good for an unshielded transformer. And then a simple rectifier and filter, and 15-volt regulators on heat sinks. So that's the power supply board, and I'll show you that later.
This is the analog schematic, and it shows the 4 output channels. On the right we have the 4 output connectors. Each one has a force high, force low, sense high, sense low, and a guard. So there's 5 pins on each one, and those are pluggable screw terminals. So you can screw wires into the screw terminals and then plug them into the board, and they can be interchanged easily. The 5th connector, the top one, J3, is a system calibration connector, and that's hooked to the system sense and the system force connectors. So that's used for calibration typically. On the AD5522, there's 4 identical channels. Each channel consists of sense and force signals. It has the high current sense resistor, which is a 20 ohm resistor on each channel. And then there are 2 compensation capacitors, and there's an optional jumper to select 2 larger value capacitors. So typically the compensation capacitors are designed to make the chip operate as fast as possible with no capacitive load. But if a capacitive load is used, compensation capacitors need to be increased. And as you see, there's 4 of those, and those are all 4 are identical. On the left side of the chip, we have the SPI interface for serial communications and a couple of power supplies and grounds. On the right side of the chip, on the upper corner, we have the measure output pins, which feed the A to D converter up here. And the A to D is AD5685, and that's a fast 16-bit A to D converter. It uses the same SPI bus, so clock and data in are the same. SDO connects to the SDO on the other chip through a jumper, but they are the same signal. And there's one additional signal, which is the convert ADC, which tells the ADC to perform a conversion. On the upper left corner, we have the voltage reference, and that's a precision 5-volt voltage reference, and that's a 3 parts per million per degree C temperature stability. So it's quite good. And the rest of the caps are just bypass caps. Oh yeah, the system force and system sense signals are over here on the right. 5-volt reference goes in, reset, and a temperature alarm pin. And I don't currently do anything with the temperature alarm pin. I'll probably pull the temperature in software periodically to know whether there's a dangerous temperature condition. This is the other sheet of the mainboard schematic, and it contains the CPU, the isolation circuitry, the EEPROM, the front panel, a bunch of connectors. It has the front panel, optional Nextion display, the SPI, the OLED display, power, processing, and the fan control. We'll start with the CPU. For the CPU, I chose the Adafruit Itsy Bitsy M0 Express. I like that it's an ARM processor, 32 bits, has plenty of memory, and it actually has more I/O than their Feather series, and it costs less. I thought it was a good choice for this project. The reason it has more I/O is because it has more pins on the sides, but in addition it has 5 pins on the bottom, which bring out a couple of extra I/Os, and it also brings out the debug pins if you want to use a debugger. Above that we have the EEPROM, and that's an interesting story. I thought the M0 Express had EEPROM on chip, and I discovered by trying to write Arduino code for the EEPROM that it didn't have it. And there's another approach you can use is to dedicate a small block of flash memory as EEPROM, and there's libraries for that. And I thought, oh, that'll work, no problem. But it turns out Arduino clears the flash every time you download a new program, which you do fairly regularly, especially when you're developing the project. So anyway, that's not acceptable. I was losing my calibration data every time I uploaded the program. That's no good. So I finally decided it's worth the 40 cents and two I/O pins, since I was going to probably use I2C for something else anyway. So I used the I2C pins and an external 24C CS08, which is 8 kilobits, so 1K by 8 EEPROM. For isolation, I like the SI series. I use the SI8861, which has 5 transmit channels and 1 receive channel. And I'm not looking for super high voltage, so I use the narrow package, which these come in narrow or wide 16-pin SO. And you can see that it's passing the SPI signals and the conversion pulse for the A to D, and it returns MISO, which is the serial data out from the A to D and from the AD5522. I put a spare package on the board so that I could put additional channels if I decided I needed them, but currently I'm not using them. And you can see that there's already one spare transmit channel on the top one. The rest of the board is the connectors and the power. This connector is for the front panel. That's a 16-pin, runs off 3.3 volts, provides 3.3 volts and a couple of grounds. The front panel is implemented as a matrix of 16 switches. So there's four columns and 4 rows. The rows are individual I/O signals that are read, and the columns are decoded on the front panel board using these 2 wires. So CA0 and CA1 are column address 0 and column address 1, and they select the two wires select the 4 columns. The LEDs are bidirectional, and I came up with a trick to drive bidirectional LEDs off a single I/O pin, and then there's a I2C on here just for future expansion. It's always nice to have I2C on front panel and controls. Next connector down is an optional serial port for controlling the Nextion display, and that gets 5 volts and transmit and receive from a UART. Next connector down is the SPI OLED connector, and that shares the SPI with the other SPI devices, and it has its own reset, DC, and chip select. And those require individual pins. Over here we have the input power connector, and that's 4 wires, nominally plus minus 15, but you can also provide an optional plus 20 to drive the DC to DC converter. All the plus minus 15 and this plus 5 down here are all isolated. But to create the non-isolated power supply, I had to take some of the isolated power supplies and build an isolated DC to DC converter to make 5 volts. And then 5 volts is used to provide power to the CPU, the front panel, and the fan. I didn't want to have the fan on the isolated side. I wanted to have it on the non-isolated side, so I chose to use a 5-volt fan. And this is a wide range input DC to DC. It can take anywhere from, I don't know, a little under 12 to well over 24 volts, and that converts it to 5 volts. Down here is a low current linear regulator for driving 5 volts into the isolated side for the A to D and the 5522. And that's pretty much it for this page of the schematic.
This is the front panel board, which has all the front panel switches. So there are 5 and 8 is 13 switches, plus the encoder. And the encoder is not shown on the 3D model, but that has 3 switches, one for the A, one for the B, and one for the press switch. And then there are 4 LEDs, and those are bidirectional LEDs. So here's the schematic. The switches are arranged, if you look over here on the right side, you'll see 4 columns, column 0, 1, 2, 3, and each column is driven by a decoder, and those are driven low. The decoder drives one of those 4 signals low at a time. When it drives it low, if the switch is on, then the corresponding row signal is also pulled low, and that's how it detects that a switch is being pressed. The encoder is just treated as 3 switches. Notice the common signal C0 goes to the switch on the encoder, and it also goes to the A and B signals. It's hooked to the C pin, or the common pin for the A and B encoder outputs. So really, it just looks like 3 more switches, 3 more momentary switches. The reason for the diodes is that the diodes provide isolation between the different columns. So you can drive one column low at a time without worrying about pushing multiple switches and either shorting to another column, which would be bad. By the way, usually the columns are open drain or open collector to prevent that from happening. Because I use diodes, I didn't have to use the open drain signals. And the diodes provide a neat feature of isolation where you can push multiple switches at the same time and detect them properly without any so-called shadowing. You know, for example, if I push 2 different switches on 2 different rows and 2 different columns, then the software would couldn't distinguish between some of the other rows and columns in the matrix. Whereas by using diodes, you have complete isolation from every switch, which is nice. So, you know, I don't know what
what the switch combinations I'm going to want are, but for example, for calibration or for other more advanced features, I might want to use multiple push buttons at the same time, and this allows that. And the cost is 16 diodes, 8 dual diodes, and each dual diode is about 10 cents. So it's about 80 cents worth of parts, and it makes the keyboard a lot more flexible. Then the LEDs, I use 220, 220 pull up, pull down, and the LED pins from the processor will either be tri-state, in which case both LEDs are off, low, in which case one of the LEDs will be on, one color, or high, in which case the other LED will be on. And this circuit has a slight disadvantage that it draws, I don't know, 6 or 8 milliamps per LED when the signals are idle. I may be able to increase the resistances from 220 ohms to something larger and reduce the current a little bit. It was the easiest way I could see to control 8 LEDs with 4 wires.
So that's the end of part 1 of this project. Part 2, I'll be discussing the implementation of the real circuit boards and demonstrating how it's working so far. If you're interested in pursuing this project further, you can go to my website at www.djerickson.com/quad-SMU. There you'll find a lot more details on the design and the design files as well. Thank you for watching. Hope you enjoyed it. Don't forget to give me a thumbs up if you like this video, and feel free to subscribe. Thank you very much.